Dr. Jason Box is a glaciologist at the Bird Polar Research Center at Ohio State and also has an appointment at the Geological Survey of Denmark and Greenland. Here he is. I'm not sure what that is, but I'm sure he'll tell us. Maybe it's a glacial lake. I'm not sure. He has had boots on the ground in Greenland 23 times, and he was recently featured for this in the hit documentary Chasing Ice, which I'm sure many of you have seen. So for the perspective of the man who is much explorer as scientist and who has been there himself and can tell us about it, I'm going to give you now Jason Box, and I have to toggle quickly in order to get his presentation working. But Jason, thank you.
Thanks, Chris, and it's great to be here. I want to set up addressing that question, is Greenland lost, first by talking about Greenland's dynamism and its climate interactions. For me, the story began with 11 years of installing and maintaining a network of climate stations on the inland ice of Greenland. That had me traveling around each year doing a tour of Greenland, trying to keep these climate observing stations operating. And I'm happy to say that even today, after about 17 years, many of these stations are still operating, and a number of people work on maintaining them. During that time, the story of melt, the question of how much melting on Greenland, that became a driving question in our research. And here, examining the many surface melt lakes that appear on Greenland, brought us to these lakes to understand them as solar collectors, as reservoirs of not only water but heat that warms the ice internally when they drain. We conducted surveys on these lakes, and were able to place the role of lakes in a climate context through externally reviewed publications. The lakes also drain, and this is a very dramatic event when you get a Niagara Falls type flow into the ice sheet. Sometimes it's a trickle, sometimes a great torrent, and of course, so you want to minimize your time spent on the lakes because you don't know when they might drain. I was fortunate, privileged in an ominous way to visit far north Greenland, then the largest ice shelf in the Arctic on Petermann Glacier in northern Greenland, and to see with my own eyes this great ice shelf retreat 15 miles in a single event that detached a floating piece about 4 times the area of Manhattan Island. And you may notice, if you look upstream of that broken piece on the right side in the year 2010, there's a big crack. And so it was easy to predict that there should be another great detachment from the Petermann ice shelf. And indeed, it was just 2 years later that occurred, this piece larger than Manhattan Island, breaking off in a record-setting warm summer, which begs the question, well, was it climate that triggered this? And it's not so simple. We need to understand the role of meltwater on the surface of an ice shelf exerting a force downward and pushing apart cracks. That's a mechanism we call hydrofracture that makes it possible for melts to produce this type of change, and that science is still underway. Petermann's loss looked like this, and considering previous surveys going back even into the 19th century, this was a new minimum for the front of this large outlet to the inland ice sheet reservoir. Through surveying the other 39 widest glaciers in Greenland, we find that 8/10 of the area losses are in the north of Greenland. That's where the ice shelves are. And Petermann is not alone in losing large areas. I used to say that this was the sleeping giants of Greenland awakening, but it's clear to me now that these giants are awake, and they seem to have a bit of a hangover. Each year visiting Swiss Camp, we flew over the world's fastest glacier. It's about 4 miles wide. And that area that you can see, I didn't know at the time in 2002, but a large ice shelf disintegration had just begun. This photo from 2002. Here's a satellite image from 2001. And by 2010, the Jakobshavn Glacier, or Ilulissat Glacier, had lost an area greater than Manhattan Island once again, while doubling in speed. When glaciers lose ice shelves, it's like removing a doorstop from a door, and the door can fly open. A lot less flow resistance, the ice speeds up. So we have a doubling in the discharge of the world's fastest continuously flowing glacier, and contributing to loss of and drawdown of the inland ice sheet reservoir. The effective retreat of this glacier is about 10 miles in as many years. The widest 40 glaciers in Greenland in the last 12 years have lost an area equivalent with the District of Columbia, DC. That's 1,700, nearly 76 square kilometers. The area of DC lost in the last 12 years from the front of a collection of 40 glaciers around Greenland. As to the question of Greenland's marine instability, if an ice sheet is marine-based, like the West Antarctic ice sheet, which is more marine-based than Greenland, it's fair to recognize that the Greenland ice sheet also has some marine instability built into it. This graphic illustrates the Greenland without the ice, the bedrock, and the blue areas are below sea level. The Petermann Glacier, the Humboldt Glacier, the 79, and the Ilulissat Glacier, these are the big outlets to the inland ice sheet reservoir. They have areas that are below sea level that go to the thickest parts of the ice sheet. So there is some marine instability to Greenland, not just the West Antarctic ice sheet. Rewinding a bit, 5 years ago, I suppose, and this is an important point about, we recognize that there's this pattern of increasing temperatures globally. We call it global warming. And I published, well, what's Greenland doing relative to the Northern Hemisphere? The Northern Hemisphere is in red line, the Greenland's in blue. Greenland's fluctuating more because that's a regional change. And we, in 2008, 2009, when we published this, we speculated that Greenland was actually needed to warm a whole lot more just to be in sync with the Northern Hemisphere climate. And so to kind of test that claim that we made back then, we can look at now the subsequent years. So here's through 2006. Watch the blue line, Greenland, 2007, 8, 9, 10. And I need to update this graphic through the record-setting 2012, but you can see how, indeed, Greenland's temperatures are rocketing up to just be in sync with the Northern Hemisphere climate, and this should produce another about 0.6 degrees of warming in Greenland. That, if you can see on the vertical axis on the left, Greenland's temperatures are now above 1 degree higher than the 1951 to 1980 baseline, and it seems catching up with the Northern Hemisphere warming pattern. But of course, as you know, Northern Hemispheric temperatures continue to rise, and it's not yet clear to me if Greenland has fully caught up, or will it catch up ever. Sea ice decline around Greenland. It's interesting to notice in winter and spring, about half of the sea ice is gone just in the last decade. This has implications to the stability of its glaciers. Those red colors, orange colors indicate the decline in sea ice. Sea surface temperatures in summer around Greenland have been elevating in the recent decades. So there's a clear signal that Greenland's climate is being perturbed. It's become really interesting to look at the reflectivity of the ice because that responds to the heat. Heating, it rounds the crystals and makes them simply darker. And if there's melting, you know how wet sand is darker than dry sand. It's similar with snow. And in just the last 13 summers, you see 2000 here. I'm going to forward to, this is the reflectivity or whiteness of the ice sheet. Here's 2000, here's 2012 in summer. I'll go back to 2012. The ice sheet is getting darker because of heating, again, which drives a metamorphic change of the ice crystal shape and melting. And also, as I'll talk about a little later, wildfire soot and its role in darkening the ice sheet is a more open question that we're trying to answer. Here's what the seasonal variation of the reflectivity of the ice sheet looks like through time. And the ice sheet gets less reflective in summer as, again, heating and melting draw down the reflectivity of the ice sheet surface. The black line is the year 2012, when the Greenland ice sheet reflectivity drops to a new minimum in the satellite record that goes back 13 years. It was exciting to communicate this story because as it unfolded, we were updating a blog and we kept being surprised at how dark the surface of the ice sheet was getting. And we have this wonderful capability, thanks to our satellite constellation, of being able to monitor the ice sheets near real time. This is a longer climate reconstruction. It's 172 years of summer temperatures for the Greenland ice sheet. That we now find Greenland's temperatures are poking above any previous time in the observational record. 172 years. And because the Little Ice Age is on the left side of this, the 1850s were the end of the Little Ice Age, we can deduce that the recent decade in Greenland is probably the warmest since the Norse settled Greenland about 1,000 years before. And to put more precision on that, using gas trapped in bubbles in an ice core, the blue line is a reconstruction of Greenland's temperatures. The black line, which is a little hard to see, is on the right side. That's that temperature reconstruction you just saw based on weather station records. And then finally, the red line on the far right is the 23 years of actual weather station observations. You can see the little photo of the weather station there from the top of the Greenland ice sheet. The red line that indicates that temperatures recently are just beginning to rival those of the medieval warm period, if not exceed those. This graphic illustrates the abrupt rise in global temperatures that we understand is forced by human activity overloading the atmosphere with heat-trapping greenhouse gases. This graphic has been dubbed the hockey stick because of its abrupt departure from climate of the pre-industrial time to this temperature which is rocketing upward. That the red line illustrates the instrumental temperature record from weather stations, and then the other lines illustrate reconstructions from a variety of pre-instrumental thermometers. And now that this hockey stick has been confirmed in independent lines of evidence, it appears to be accurate, and the implications are that humans are perturbing Earth's climate in a very profound, abrupt way. And I say this in looking at the Greenland reconstruction from the previous slide, that we are just now starting to punch above the natural variability of the past. And that is driving an enormous charging of energy into the global oceans that is equivalent to 2 Hiroshima little boys per second over time in the last decades. That represents the energy imbalance of our climate system. 8/10 of that's going into ocean heating, into this massive heat reservoir, and the heating of the oceans represents a factor that is likely to, if not already, be destabilizing marine-based ice sheets, Antarctica and Greenland. And all of this is driven by the abrupt increase in these so-called greenhouse gases. We are currently 40% above the peak Eemian values, or the pre-industrial values for CO2, plus 40%, plus 246% for methane, plus 17% for nitrous oxide. This is the hockey stick in greenhouse gases that is driving the Greenland response. Greenland becomes a valuable indicator of change because it's being forced really externally by the surrounding global climate. And so Greenland is a useful laboratory to indicate change, to sense change. And of course it's more than that. Greenland has sea level influence, and also influences North Atlantic ocean salinity, which influences global climate and influences North Atlantic and European climate, to say just the beginning of the story. So this perturbation to Greenland's climate has produced some surprising changes. The dramatic video of a tractor being washed off of a bridge that was built 50 years earlier in Greenland, the river topping over this bridge, clear evidence that the Greenland's ice is responding to this perturbation of global and regional climate. That the bottom line is some measure for Greenland is its sea level contribution, and what we've observed in the recent decade of satellite observations is a doubling of the rate of sea level contribution from Greenland. We start to see the non-linear aspect of the response of the ice sheet to this perturbation, the doubling of surface melting in the last decade, the doubling of absorbed solar energy in the summertime, the doubling of the ice loss. These doublings again represent, and it's a way for us to understand, because we tend to think in linear ways that it's the doubling that can, occurring over time, produce change that is of relevance today and in the near future for policy to address this issue of we need to stop and even reverse the trends of adding greenhouse gases to the atmosphere. For a longer perspective on sea level, this goes back almost 2,000 years, and what you see is that bump in the middle is from the medieval warm period. The cooling from in the Little Ice Age to the right of that bump in the middle of the graphic, that's a drawdown of sea level from ice building up in glaciers once again. And then the recent uptick and the instrumental record you see with that darker black line, that illustrates where we've come in the last 2,000 years. And to the right of the vertical line is where we expect we'll be in the next century, and that gives perspective of this hockey stick in sea level that's that has just begun. And we start to approach the question of, okay, what's the rate of sea level rise? And how important is that today and in the near future, and how relevant is that as a policy question is what I look forward to our discussion after this this foundation. Incidentally, when we really connect the dots about current atmospheric CO2 concentrations in the past history of sea level, we find that for climate just to be in equilibrium with the 395 parts per million of CO2, just to be in equilibrium, global sea level should rise 21 meters. That's for today's CO2 level. A 69 feet in global rise in global sea level, just to be in equilibrium with the greenhouse forcing that our activity has produced so far. And of course, greenhouse gas levels are rising still. This relationship is corroborated by the past paleo record from ice cores and ocean sediment records that indeed show really vast sea level changes associated with dialing greenhouse gases up and down. And of course, in the past, the ice ages cycles were forced by orbital variations. But what's different today is that human activity has become the dominant climate forcing. And that's unique in Earth's history that we know so the past records are only so useful for us to understand the past. But what's again different now is that humans are the driving force. And we don't fully understand what types of changes that occur, that produces in sea level and other changes in the climate system. This brings me to the point of there's a lot of feedback processes and then multipliers to the feedbacks. The feedbacks, that's self-reinforcing physical processes that produce nonlinear abrupt changes, responses to a perturbation. These are operating and these produce surprising changes. There's also multipliers within those feedbacks that we don't fully understand these yet. And I'd like to just bring you through one of these cases and then looking forward to discussion. That's the role of wildfire that is occurring now in the Arctic at a higher rate than it did before. Fire is a natural process in the climate system, but there's evidence that wildfire is increasing not just in the lower latitudes where we live, but on Arctic tundra burning. And the question of what role does this play as the dark black carbon soot as a multiplier in reflectivity feedbacks, that's a question that's very exciting to ask right now. Feedbacks with the reflectivity of the cryosphere, the snow and ice, and result from both changes in temperature, which are driven by, so on the upper left we've got fossil fuel combustion, that's heating climate, that's increasing air temperature, that is increasing wildfire incidence. It's also darkening snow surface because of metamorphic thermal effects. The wildfires also then, which leads to additional heating, and at the same time industrial fossil fuel combustion is releasing soot into the atmosphere, also darkening the cryosphere. These are pieces of feedbacks that again amplify. This isn't a runaway cycle, it's just an amplifier. But how much soot amplifies warming is just starting to become better appreciated. Soot just got elevated above methane in terms of its heating importance just a week ago in an important study published trying to document this very complex issue of aerosols and climate. We have, again, wonderful satellites to monitor fire daily. This is a map of daily fire data from NASA that we're working with, and here's just one fire that we linked using another satellite sensor from NASA and the French Space Agency. We see smoke drifting over the Greenland ice sheet. So we founded a campaign to better understand the role of wildfire in darkening the ice sheet, called Dark Snow Project, where we're currently crowdfunding, trying to reach a funding goals to launch a science campaign in Greenland this coming summer designed to put the role of fire in better context. We know that reflectivity has declined, but how much is wildfire soot contributing to that is an example of how we use Greenland as a laboratory to answer a climate question and to add detail to what we don't fully understand, the effect of and the rapidity of abrupt climate change in Greenland. So to finally get to the question, is Greenland lost? You've seen that ocean heat content has been elevated greatly. You see abrupt climate change is underway. We see Greenland's temperatures, I would say, rocketing upwards just to be in sync with the northern hemisphere, and which itself is warming due to overloaded greenhouse gas concentrations. The question is, Greenland ice loss can be defined as it has been in the past. When does the surface mass balance become negative? The surface mass balance is the balance between snowfall on the one hand and meltwater runoff on the other. And without sufficient supply of snowfall, there's less mass going in. If the melt increases more than there's snowfall, that's the point when the surface mass balance becomes negative. Any healthy glacier always has a positive surface mass balance. There's always more snowfall than melt, and that causes a glacier to grow. When there's more melt than snowfall, there's no dispute that ice body is on its way out. And the year 2012 was the first year, arguably in at least in about 800 years, that the surface mass balance of Greenland was negative. 2012, the first year where Greenland is beyond its viability threshold. So if 2012 climate continues, we have to take scenarios when we consider the future. Greenland would steadily, continue to lose about 600 billion metric tons per year, and that would dispose of the ice sheet in 1 or 2 times 10,000 years, so a long period of time. That's with a constant 2012. When, of course, a more accurate scenario is one of Arctic climate warming, somewhere between 4 and 12 Celsius above the pre-industrial times. At that point, Greenland's far beyond its viability threshold, and we see these feedbacks kicking in ways that turn that 600 gigaton, 1 millimeter per year sea level loss per year. We see that doubling and doubling again and doubling, and it's conceivable to see by end of this century something like 4 to 6 feet of sea level rise. But the uncertainties are so large that no scientists are really claiming any precise numbers because we don't know all of the physics yet. We can think back on that, what we understand that the current greenhouse gases should produce 20 meters of sea level rise, which obviously implies it takes time for the ice sheets to decant that much mass. But what we don't have a good handle on is how fast that happens. Do we see 1, 2, 3 meters of sea level this century is still a difficult to pinpoint question. We understand Greenland a lot better than we do Antarctica, and so the science in Greenland is applicable in Antarctica. As Antarctica presumably starts to melt more on its surface. It doesn't melt very much at the surface today. So the question of is Greenland ice lost depends on how long the ice spends its time beyond its viability threshold, which is it's been quantified to about 1.6 Celsius. We're at about 1.1. We're very close, or if not at the viability threshold, because after all, year 2012 was, if 2012 continued, we obviously are already beyond Greenland's viability threshold. The question really is, does Greenland's climate get pushed far beyond its viability threshold? How long does that get sustained really depends on if we can bring atmospheric greenhouse gases down somewhat. The more we can cool climate, the slower the Greenland's loss will be. If Greenland remains above its viability threshold for long enough for the dynamic thinning to slump the ice sheet down into lower parts of the atmosphere, at some point it does become irreversible. It takes a whole ice age to regrow the ice sheet. Sustained cold over many thousands of years to regrow the ice sheet. It certainly at some point is lost. I think that humans have some degree of choice in the matter, whether we allow greenhouse gases to increase business as usual, or do we ratchet them down, as has been recommended by scientists for more than 2 decades now. I think the discussion will be even more interesting. Thanks for your attention.
Okay, and let's hope let's hope I don't feedback, and I already am. So let me come over here and try to use the podium mic. Thanks so much, Jason, and I think that was deeply informative and frightening. The first question that I got to ask you is there, I already mentioned it, there's this new study. Is there any consolation there? I mean, it seems to suggest that somehow a lot of melting occurs and then a stability is hit. But the climate we're heading into is not necessarily the same as the climate back in the Eemian, which you'll tell me how many years ago it was. So is there any consolation?
Well, at the present time, Greenland is losing ice at more than twice the rate of Antarctica, and that's going to take some time. If at the West Antarctic ice sheet really starts to go, we will see Antarctica taking over that lead position of biggest loser, and meanwhile, Greenland, I think, will still be a contender, if you will. And of course, our greater concern is about not just the ice sheets, but other land ice, and how smaller glaciers and ice caps have been contributing more than Antarctica in recent decades as well. So until that switchover occurs, we can't say with that much confidence that Antarctica is the only thing to pay attention to. Obviously, we want to pay attention to all sources of sea level change, including thermal expansion. Another point that's worth making is, again, the difference between the current climate, the Anthropocene, and the Eemian. That's 126,000 years ago, when this recent study shows that the temperatures in Greenland were between 5 and 8 Celsius above the last millennium. Greenland's temperatures today are about 1.8 Celsius above the past millennium, and heading upwards. And Greenland's already a significant contributor to the just beginning to accelerate sea level change. We need to continue to use Greenland as a laboratory to understand physical processes, because Greenland is relatively well known what's happening. Antarctica, much more vast. It as has been shown before, changes in snowfall over Antarctica can significantly moderate its mass loss. There's certainly more to that question.
Mm-hmm. But let me get on the mic again. But just to follow up, we're going beyond. At least we already are beyond in terms of greenhouse gases. The Eemian, where they just found that Greenland was still there.
Right.
So
yeah, CO2 is 40% above Eemian. methane 240% above, and that's different. There is no analog for that in the ice core record. So, and the feedbacks with human activity of biomass burning, the soot that releases, that presumably was not happening in the Eemian. That's another, just an example of a factor that's different today than at that time.
Okay. Do we have any questions that folks want to ask following up on this? Yes, please. So please identify yourself, and then since you're not mic'd, I or Jason, we're going to try to repeat your question so that everybody picks it up, and then we'll address it.
I have a lot of questions, but I share the time. My name is Rafe Pomerantz. Two questions. First off, one is apparently one of the reasons for surface warming in Greenland is the change, or maybe the Arctic amplification affecting the way the summers are warmer because ridges are going further north. So then a little bit more about the massive warming of the oceans and this imbalance, what that is, and how I mean, supposing you stabilize greenhouse gases at today's levels, what would you expect to happen to temperature and sea level rise? I would like to go back to the issue of policy around aggression. Sea level rise.
Okay. Current warming, if I'm getting this right, might be affecting the jet stream, which in turn would be affecting what's happening in Greenland, and then secondarily asking for more information about how the warming that's in the oceans that is implied, it implies a certain higher level of sea level than we currently have, how that's playing out. Does that seem fair? Okay, so go.
Yeah, great questions. And Greenland's recent rapid melting has a lot to do with atmospheric circulation anomalies that produce a lot of south air flow over the ice sheet, and that is related to the jet stream, the planetary wave circulation, locking in this type of pattern for the past 6 summers in a row over Greenland. And there's mounting evidence that the decline of Arctic sea ice and the decline of snow cover on land is an important part of that story. That even the cold air outbreak that we just had in the U.S. is linked to a pattern called warm Arctic, cold continents, and how the decline of Arctic sea ice it appears to be disrupting planetary circulation in ways that give us persistent drought, rain, heat, and cold. That's definitely part of the story, and Greenland is just occupies its corner of the world that feels that, just like we do here in the U.S. and in Europe, and a lot of recent global regional climate events like the fires in Russia, the Pakistani floods, the winter without the year without winter last year in the upper Midwest U.S. These are all part of this disrupted jet stream issue that I think Greenland's just kind of falling somewhat victim to. The 2012 melting in Greenland probably doesn't reflect the recent average. It's because of this perturbed atmospheric circulation that has persisted for 6 summers in a row. This might be the new normal. 2013 summer, I'm sure on our minds, is that going to produce the same kind of melting in Greenland? I think it's more likely than not. We'll have to see. Your other question was about increasing ocean heat content, and that's eroding ice sheets from below. A lot of the ice sheets is marine terminating, so we have marine-based ice. That warming ocean packs a much greater punch for eroding ice than atmospheric warming does. Arguably, the climate change story is primarily one of ocean climate change, because the planet is 7/10 covered by ocean, and that ocean is uptaking 8/10 of the planetary heat imbalance. That is destabilizing the ice sheets. That's definitely part of the story. How much it leads to Greenland glaciers retreating into their marine-based outlets is something that actually we're just now beginning to be able to model. The physics of the West Antarctic ice sheet disintegrating are more complex. That problem is less well constrained. There are, as some have put it, more unknown unknowns in Antarctica, whereas in Greenland we have more known unknowns. And so Greenland becomes more modelable, if you will, and a useful analog to understand the effect of ocean heating on destabilizing ice sheets. Perhaps we can talk about policy in a broader context after other questions.
Other questions? Anybody? Got one right there, yes?
Nick Sunt with WWF. Are you seeing changes in ocean circulation around Greenland?
The question.
Oh, you can restate the question.
The question is, have we observed changing ocean circulation around Greenland? And there have been some pulses of warm water that have destabilized Greenland glaciers, led to some very dramatic doublings in speed around all of South Greenland. That may just be the weather of the ocean, but if the ocean heat content is elevating, then those ocean weather systems are obviously growing in a system that has changed. Monitoring ocean circulation is obviously very important, and I don't know a lot more about it than that. There's a growing movement, if you will, of field observations that is targeted at understanding the role of ice-ocean interactions, and that's a very important frontier in glaciology today.
Yes, another question.
Josh Landis from Climate Nexus. A lot of the people who are resisting the body of evidence of global warming like to cherry pick facts and figures, and I saw one in your presentation talking about Greenland is as warm or warmer than it was 840 some years ago. So to someone who would say, ha, look, 850 years ago it was just as warm as it is today, how could it be human-driven climate change?
Well, a question about basically cycles and what climate skeptics say. They always say there was a point in the past that was this hot, so therefore don't worry now, and you pointed out one from his talk, so I guess he'll respond.
Yeah, it's true. Climate has had its cycles in the past. The short answer is that now human activity is the driver, and that's superimposing the impact that we have on climate on the whatever cycles may still be happening. We are just imprinting on top of that. So it's flawed logic to point to the medieval warm period and say, well, see, it was warm then, and that it reflects a misunderstanding of the fact that human activity, alteration of atmospheric chemistry, has become a driving force in climate change.
I'm going to take the liberty of asking another question because I think it's implied here, and forgive me for sounding a little radical, but we're messing with big things we don't fully understand. And one could imagine there would come a time when scientists like yourself would say, I don't know if we're in that time yet, you would say emergency. In other words, you'd say, all right, this is starting to go really fast, and if it doesn't stop, and this could be Greenland or West Antarctica, I can see now that the sea level is coming fast, and fast in relative terms, right, but it's coming. Somebody has to decide quick if we want to take a more radical measure to try to stop this, because it really means meters. All right, what are you going to do with a planet like that? So do you want to put reflective aerosols in the stratosphere and start trying to cool things down quick? Because the kind of change you're talking about, so many people live in these places. What would the moment be? What would it look like when scientists finally say to policymakers, emergency? Or is that too radical a question?
Well, it's a difficult question
Yeah.
because there's a lot of unknown impacts of active alterations of climate. Arguably, humans have conducted an inadvertent climate engineering already, and what you're talking about is, okay, do we step in and say, okay, this is what we understand about climate? Can we cool climate on the short term. And fortunately, there are ways to do that that are kind of win-win strategies by simply, or not so simply, reducing soot produced by biomass burning from people heating and cooking. On the short term can really take the bite out of climate change in a way that we don't have to launch, high-tech stratosphere reflection kind of campaigns. We need to provide technologies of cleaner burning stoves to much of the developing world, and that's going to take a wedge out of the problem on the short term. With on-the-shelf technology, we just have to roll it out and help the developing world get to the point where they're not releasing so much carbon soot into the atmosphere. And with a combination of other wedges, efficiency, renewable energy, leaving fossil fuels in the ground, have a lot of co-benefits. Less fossil fuel combustion, again, less soot, which is giving people respiratory problems. There's plenty of other pollutants in diesel soot that are making people sick. And we have, again, on-the-shelf technology for renewables that can deliver a lot of our energy needs. We just have to make that transition as quickly as we can to avoid Greenland, keeping Greenland above its temperature threshold. I think that's within reach, but it requires us getting past the politics of the problem and recognizing that the livelihoods of our children depend on us being proactive about their futures.
Couple more hands. So, just since you haven't asked one yet, here.
Yeah. You said something that I haven't identified. Yeah. I'm Peter Sinclair, Climate Denial Cracker Week. You said something, and we've had a lot of conversations, and I haven't heard you say this, in regard to the 21 meters of sea level rise just to bring us into equilibrium, if I understand correctly, with conditions that already exist.
Right.
Let me just restate that, or do you want to restate it? He's just asking for elaboration on what I thought was also one of the most striking slides. Basically, that current concentrations of greenhouse gases in the atmosphere imply a dramatic level of sea level that I've never heard they imply before, which is already many, many feet.
That's right, and it obviously takes time for land ice to respond to this really abrupt change in the heat balance of our planet. We're talking about the atmosphere and its capacity to trap infrared radiation that's emitted from the surface when sunlight shines through, heats the surface. That's good. That keeps our climate, within the livable temperatures. So the greenhouse effect is a good thing, but too much of a good thing produces the kind of overheating that will melt current concentrations of greenhouse gases. If the climate could just equilibrate with them, would already raise global sea level by more than 20 meters. That's with today's greenhouse gas amounts. The question becomes, how quickly does that occur? And I don't think you'll be surprised to know it takes a long time for that to happen. That illustrates, humans in geologic time are exerting themselves a force that is applied in an extremely abrupt way. And so the climate system has been hit really hard, like with a hammer, and how it adjusts or readjusts, reconfigures to this perturbation is the central problem in climate change science. It's basic physics to understand that the atmosphere will heat. We should expect ice sheets to melt, as they have done in the past under elevated greenhouse gas conditions. That's it's kind of an awful truth of the data that we are that far beyond the threshold already. But we should never use that as a reason to say that it's beyond hope, because we always have a choice between a high and a low emission future. We have a choice between whether we go business as usual or decide on technologies and energy policy that brings our emission way down and has that takes the edge off of that steeply rising curve, and through those stabilization wedges we can actually reduce. We can bring the curve and down into the direction that we need to.
Okay, we got still a little more time, so Rafe again.
Thank you. Great discussion. I want to come back to the policy and your point. First of all, in order to know if Greenland's lost or if it can be saved, you really have to compare, to the extent we can model estimates of future emissions and concentrations, right? And what the best case is, what the business as usual case is. And these days, best case, business as usual, maybe best case is 500 parts per million CO2, 450 if you're, right? Maybe more. Pick your number, because we're about 400 now. Then you'd have to compare the sea level rise to the hit that American cities take. I like to say Miami is Greenland. Miami's at sea level, it's limestone, you cannot build seawalls. And it means that the water table is the Atlantic Ocean. It's kind of inundated. And so it has a sensitivity in the inches. The whole region does. It varies. And then you'd have to compare that emissions scenario, to the impacts. And back to Chris's point, we don't have a government-based analysis of the role that managing solar radiation could play if it was required. If it was required. And this seems to me to be a hole in research. There are people modeling it now, but that's different than the policymakers actually understanding what the choices are, because if you pull the emergency cord and you had to look at this, we don't have any guidance whatsoever in the U.S. government. And we don't have an analysis. We do some research, but we don't have an analysis. So I think I'm suggesting a policy approach, which is compare the scenarios of emissions and concentrations to the impacts of sea level rise, and then look at the forcing changes you could get if you had to intervene with solar radiation, and see what that did to sea level rise. I think we're actually now have approached this question because the rate of decline of Greenland forces the issue to look a lot more closely at sea level rise, because the estimates of the rate of increase have gone up 3 feet, 4 feet by the end of the century. But there's a lot of places where the sensitivity is way lower. And that hasn't gone on the community yet. And so let me put that, that's a comment, but it's also a question. Isn't that what you have to do, is compare your best estimates under one scenario with another? Sea level rise, not temperature, sea level rise.
You want to try to summarize that one? Answer.
It's a long-winded version of...
To make realistic the kind of thinking that would have to occur if we're actually going to respond to scientists saying emergency, and it sounds like policy system isn't built for that, and that's what is behind the question. So then he's outlining ways in which, if it was rational and it was built for that, considerations would be brought to bear. How's that?
Given the let's say maturing body of climate science, climate change science, it's obviously now in the policymakers' hands to do something, something that addresses the risks, and to examine sea level rise in terms of risks. And the insurance industry does this professionally. We can learn from insurance and because this is a risk factor, and how do we manage this risk factor in ways that we can come out of this thing, kind of optimally. I'm not a risk management expert. I'm not a policy expert. I think, as a scientist, I just we need to hand off the science to policymakers, and then they need to forge policy and untangle themselves from political obfuscation, which is obviously getting us nowhere, leaving us behind technologically. It's a losing game if the U.S. doesn't get its act together, obviously, in terms of economic factors, not just environmental factors. So I think this is really just a challenge to policymakers, like, do your job. The scientists we've done our job. Time for you to do your job. And stop giving yourself raises until you do your job.
I think that's a good note to end on. I like that. So thank you very much, everybody, for tuning in. I know there's more questions, but you can take them offline. But I'll say goodbye to the live stream folks. So thank you so much for tuning in, and please check us out again for the next Climate Desk Live.